Hey everyone, welcome navigators. Welcome to session 4. I'll share my screen and we can make a start. Okay, hello, just wait for that to load. Okay, good. So the notes are in the Discord channel, so you should have those. Yep, I did update them. So the very first time I put them in, I realized then I'd missed a link, so I did update them. So just make sure you've got the latest ones. Right, let me make a start then. So yeah, welcome to session 4. This is all about application storage. And I mean, really, very much at the heart of what we're doing with applications. We need data, so we need to store it. I mean, it's obviously as possible in theory to have stateless applications, but in the real world, in the real things we want to do, we're going to be thinking about some way of storing some state. So today's topic. So we'll have a quick look at what's new in Mina, and then we'll. Oh dear, I've got a typo there. So have a look at the topics of storage, and particularly we'd be looking at off-chain storage and the techniques around that. I think hopefully you'll be familiar with much of this, certainly the first few pieces, but we'll go through those anyway just to make sure. And then we'll look at what I put there as other techniques. You'll see we're thinking about how we can store things. What can we do to make that easier generally? What other little tricks can we do? But then we'll look at what has come to be, I guess, really at the heart of a problem, and it's a general problem with blockchains: the idea of concurrency, and how do you, in a decentralized system, how do you make some safe decision about the ordering of events, and how do you decide about that, and how do you decide how to update state so that everybody can agree on that? So we'll look at that and the solutions to that. I'm sorry, I guess a few typos here. I'll fix these and reissue the notes. But anyway, so we'll look at some of the solutions to that, and then I'm going to sort of step back and, as I put there, look at the bigger picture, because what we're seeing in terms of the other ways to solve this are starting to mirror some of the other trends that we're seeing in blockchains and some of the architectures that we're seeing in other chains. And so I'm going to start looking at that. And that will then make more sense, I think, about some of the solutions that are coming up. And then what we'll look at, I mean, those architectures typically involve layer 2 chains. So we'll look at what is involved in those, and then we'll look at some of those solutions that are starting to be produced for Mina. And particularly we'll be looking at ProjectKit. Just going to go into that briefly today, or give an overview. I don't want to rush through that, so I'm just going to start it today, and then we'll look at it more next time as well. I'll give some more examples for that. Okay, so that's the plan. So let's get on with it. So starting off with what's new. Unfortunately, when I wrote these originally, I'd missed an article, so I'll just present that here. The what's new in 01.js or on Medium. Let me put that link into the chat. Give me a second. Okay, so there you go. Most of this, I think, a lot of this I'd covered before. We covered the hash functions that are available. So much of this, I think, you already know about, or they're sort of smaller chains. But just there's something here for you to have a look at anyway. The possibility of a lightweight, the LightNet chain as well, that you can spin up in a Docker container. So yeah, just a few updates there, but I think I've gone through most of those elsewhere. Also, I did mention last time, but just wanted to reiterate about the test world and the implications of that. So I spoke last time about I think the test world testing program had just ended. The actual test network had just about finished, I think, at that point. And so there's some details here. I mean, it's very, very impressive. And as someone who, I was involved running a node, and so I want to say thank you to everybody who organized this and did such a fantastic job. I mean, you can look at the details here and see that there's an amazing feat of organization to get everybody up and running in all these on all these locations, etc., and get everything going. So thanks everybody for organizing that. The experience of it was that there were lots of updates as they were testing, and they found issues. Then they were very quickly resolving those and issuing updates. So I think there was a lot that was found, a lot of useful work that was done in all of that. So it was very good. And of course, the reason where we're heading with this is that we have some major upgrades coming, and so there's links there to that. And this is in I think I'll link to the article there. There's links to the article so you can read there as well. But obviously, what we're going towards obviously is having contracts, and the other things. Sort of two other parts that will be happening at the same time. But obviously the first one is what we're, I guess, going to be most excited about. So that's the reason, obviously, that was being done. And then this mission generally is they're continuing as well. They're continuing with the network doing quite specific things, I think, at this point now. So it's they've done a lot of the stress testing, etc., and they're focusing on smaller items now. So that was a major achievement. Other things that have been happening as well. So this has been certainly around. I've known about it for a while. The idea of the Mina Ethereum bridge. I've got a link to from Lambda class, who do a lot of work generally in the zero knowledge area. So they've just issued this blog about that of the bridge. So you can see, so it's a good article. It shows. I took this diagram from there. Let me make it a little smaller. But the general idea is that we can get state and get proof of that. Obviously, we've got our kimchi, and we've got our curves, our pasta curves to create our proof, and we can get that, and then we can put that onto Ethereum, or I guess onto an EVM chain, and have that verified. So this brings up something that I'm going to come back to later when we talk about this kind of process generally. But the idea that we have layer one chains, and what they are increasingly doing or being used for is around security. And so part of that is to provide updates of state from other chains and put those onto the layer one chains. And because the layer one chains are seen as being more secure, they've got a very large network. It's very difficult for people to manipulate the consensus of these chains. So putting a sort of anchoring the state onto one of those is seen as a very secure way of keeping track of that state. Obviously, what we're seeing here is where we're going from one L1 to another L1. But the same sort of idea applies. And I will come back to this, but it's one phrase I heard, which I think is a useful way of looking at things, is talking about scalability, but talking about the fact that we're almost scaling the security of blockchains and allowing that to sort of expand and become more ubiquitous amongst other chains. So that's a useful way to think of it, I think. Okay, but anyway, there's an article linked there for if you want to have a look at that. Another interesting thing that I saw a few days ago is this chatbot, which could put us all out of a job. It's there. I just, if I can find the yeah, here we go. I just tried it out. So you need to I logged in via GitHub here, and when you start it up, it suggests you can either ask it questions or it suggests a question to ask. So I took their suggestion, which was about creating a simple contract, and it came up with this. So it's quite a fun thing to have a look at if you haven't seen it already, and it does give you some ideas here of what you should be doing and what you shouldn't be doing. And then it also goes on to give you an example. I haven't tried this out, so I haven't really checked that whether this works or not. I don't know if anybody has. But anyway, very interesting. I think, I mean, these tools can be very useful. And obviously, if as you know, the ecosystem grows, it's going to be very useful to be able to quickly ask questions and to be able to pinpoint areas or that you're looking for, rather than having to go through larger pieces of documentation. The only problem, I suppose, is the confidence that you have, and I don't know in this particular example how accurate it is. So that's something that I suppose we have to get experience with and make some decisions about, because the problem is that at some point you're going to have to decide whether to trust the answers that it comes back with or not, and yeah, so you need to I think, because we're being developers, then obviously we're going to be able to ask questions and be able to judge whether the answers are correct or not. And so hopefully we'll get a good idea. But anyway, so I look forward to seeing how this develops. But yeah, please do have a look at that. Have a try that out. Another thing that I realized actually after I put it in the notes, it just closed, but that could be interesting, was there was a request for proposals about ZK oracles. Now we're going to talk about these in a couple of sessions time, I think, but there's just a few details of that, being a push to get proposals around this and to standardize this. And I took a diagram from that to give you a general idea of how these things typically work. And I know that sort of back in the early days of Mina, this was always seen, and I think I put in some of the notes in session 1. I just mentioned it briefly and gave some links, but it was always seen as a very good use case for Mina, and something that could be potentially useful for a lot of people. And the reason why those people could get involved or would want to get involved in Mina is because that they could, the fact that they could then trust data that was being provided, but they'd also have the possibility of the ZK aspects as well. So yeah, but we'll come on to this more in a couple of sessions time. Excuse me. Okay, so that was just some new items that have come up. We'll go on to our main topic now. So off-chain storage. So as I say, it's in the real world, when we're writing real applications, we are very likely to want to persist some data, in order to do useful things, unless you're doing a very simple library or something, or sort of mathematics thing where you're just returning a value. It's other than that, you're very likely to want to be able to persist data. And we have a limit to the amount of storage that is available to us on chain within our contracts. And this is by design, and this really is one of the essential features of Mina. And I will talk a little bit in a minute about sort of ways to get around this, perhaps. But then you could see that we don't really want to get around this. We want to stick with this idea that our applications do have a limited amount of on-chain state, because this is essential really for how Mina works. So that is going to be a problem, and no doubt you will have, you've already come across this, and you will have come across or worked out your own ways of handling this and living with this and being able to write applications with this this type of constraints. The other point about this whole idea of off-chain storage, and well, tied in with the idea of the off-chain computation, is the fact that then that gives us things that you don't get or that are very difficult to get if you're doing things on-chain. One of which is the privacy, the zero knowledge aspect, the fact that you can have private inputs to your computation, and then you can just post an output of the computation, or a sort of summary of that on-chain, and have that validated. So that's these are really essential parts of the way that Mina has been designed. And I mean, this is also true of we're seeing this in other chains as well. If you look at what Aztec are doing now, they're coming to sort of a similar approach with the idea of off-chain computation. So it seems like this idea is something that is useful, is a valid design. But obviously, yeah, as I say, we then that does mean then that the amount of storage you have on chain is limited. And so what do we, how can we sort of continue, and how can we write useful applications given this? Well, a very sort of standard approach is the idea that on-chain, what we would have is a commitment to the data that we have off-chain. So the reason we need a commitment is because when we've done some computation, obviously we want to be able to prove that was done correctly. We want to be able, we're always wanting to be able to prove that things are being done correctly, that the state is being updated correctly. And so one way that we can do that is to provide a commitment to the state. And the reason that this is useful is that this can be very succinct. So we have functions such as hash functions, which allow us to do a succinct commitment to potentially a large amount of data. And that is, a very standard, a very typical way that people approach this. And so you would use some data structure such as a Merkle tree, which allows us to have a potentially very large data structure holding a large amount of data, but then providing commitment to that by creating a root of that data structure and then storing that. And this means that we can be sure when we're using data that we are working with the correct data, because we can check that the root, the state root of our local off-chain Merkle tree is the same as the one that we've stored on chain. And so this this gives us confidence that we are working correctly. So that's a very standard way of doing it. But if you start to, and if you're just developing this as a proof of concept, and you're just developing locally, then this this seems very straightforward and very useful. But if you start to dig into it a little bit more deeply and think about how you would do how you would productionize this, how you would do this for a larger application, then you see that we start to see some problems, or certainly some concerns and some things we need to think about. And one of them is, or one general area is around the data availability. So this off-chain storage, we've got some data that we're storing. Well, where is that going to be stored, and who is storing that? And do we trust the people who are storing this? And there are solutions to this, but that certainly is something that we need to think about. And I'll be coming back to this idea again and again, this idea of data availability. And it's not just it's not just a problem with Mina. The concept of data availability is something very fundamental that people have realized is an issue with blockchains and needs to be addressed. And we'll certainly come on to that in more detail. And what I mean about data availability is the fact that with blockchains, it's all about verifying that things have been done correctly. And as part of that, if we're looking at transactions that are happening and updates to state, we want to know what computation has been done to change some state, but we also need details of that state. So we need that state to be available somewhere. We need the data that is that forms the transactions that is changing our state. We need that data to be potentially available as well, so that we can verify that. Now, of course, with zero knowledge techniques, we can bypass some of this in the sense that we can have some private inputs, and then we can have zero knowledge proofs that this is being done correctly. But there still does need to be, we still may need this idea of data being available. And when you think about what that can actually mean, this means that people should be able to access that data. And if you think about the potential attacks of that, I've just sort of given you an example there, that somebody could claim that they've got the sort of route to some off-chain storage, but they could actually not hold any of that data. They could just hold the route and provide that, and then there wouldn't really be, we couldn't really go forward with that. You couldn't update that in any meaningful way. So it is. These concerns do need to be addressed. But if we're going to do that, and if we're going to do that in a decentralized way, it can become quite complex and quite costly. And if you look at, a very good example of this is Filecoin, who, their whole ethos is around storing data and making that available, and they heavily use zero knowledge proofs and snarks to be able to do that, to be able to prove that data is being held and is being stored and is available. So obviously there's a lot that has to be done to provide this availability and give people confidence that it's there. Now, if you have a look through the tutorial in the documentation around this, they do present some solutions to these questions. And so, if you're doing something simple yourself, then you're just going to have some single server maybe storing your data, or you're just going to be holding it locally. But that may not be a very feasible or very robust solution. So what you may want to do then is to have that data replicated, or have some multiple parties also running servers that are holding this off-chain storage. And so therefore you're not then reliant on one particular person to be updating that state. And the next point about modular blockchains I'll come on to, because this is really where we start to look at layer 2s. But it's interesting here, the idea they've got about sort of moving Mina to allow more on-chain data storage. But in order to do that, then you have to look at the sort of the game theory and to start to think about, what if people tried to do something malicious with it, try to do a denial of service, or try to use up all of the available storage. So when I say use up all the available storage, I mean sort of increase the available storage to a sort of an extent that makes it no longer practical to run a node. Because if you compare, what we want to do with Mina is to, keep it very open, very democratic, allow a lot of people to be involved with this and to be running nodes. And if you compare that to what's happened with Ethereum, where originally it was possible to run a node, but now it is very difficult because if you want to run a full node with all the data, you need, I can't remember how many tens of terabytes, but also, you have to have that. Also, it has to be fast storage as well. So obviously that's, we don't want to go down that path where data, there's no restrictions on the data that can be stored on chain. And maybe one way to help with that will be to make people pay for data, as is said there. Also, the final point there, the data storage committers, this is part of the idea around data availability, which is allowing people to provide services to make data available. But then, because we're in a decentralized world, we want to have good security guarantees about that. We don't want this to be people to be able to manipulate this, and so we have to put some guarantees around that and think about how that is going to be made secure as well. Also, I think in the notes there as well, they have some interesting suggestions also about if you're thinking about these types of solutions, some suggestions to make. So one of them, this first one still comes back to this idea about sort of the denial of service, by making it so that people cannot easily abuse the amount of storage that is available. So they would have to have a token which would have some kind of rarity, so that there would be an incentive for them not to just do an unlimited amount of storage requests. Also, the idea of being able to clean up old data. Now, some of the examples we'll come on to, you don't see this, and there are some the large applications around that don't do this, but which is understandable because it can be quite complex. But then, obviously, if you don't clear up old data, then you are potentially limiting the lifetime of your application, because one day it is going to fill up. The third point here comes back to the idea of security here. If you've got multiple servers, again, it's to prevent the idea that someone could be malicious or provide some kind of incorrect data. You would be connecting to multiple servers or multiple providers of the data to make and accepting a sort of majority opinion on that, so that you can be confident about that. The last 2 points here are sort of more practical, I guess, where you're sort of handing off the problem of scalability to other technical solutions. This sort of back to the Web 2 world, I guess, as some of these ideas as well. Okay, so that's just some points, and yeah. So I've got some questions about some of the potential areas where you can store data. So I know someone was asking about Arweave and Filecoin. Of course, yeah, these are all available, and I think it's fair to say that people have, from the sort of the start of Mina, people have been looking at these as a natural place to store data, since they are already decentralized, and that is certainly possible to some extent. I've mentioned Filecoin already and the things that they have to do to ensure that data is preserved and is available. I think in some ways the problems that we face, and what I'm going to talk about today, are less about sort of that where we are storing it exactly. It's more about the techniques and the architecture in which we are doing this. And I know someone mentioned there about Celestia, which I'll come on to as well. Okay, so but if I come back to the kind of the standard approach, I suppose, and come back to looking at the ways that this is typically done, we do, we all make a lot of use of Merkle trees, where you store some value in the leaf, which represents your data, and then this is hashed as you go up the tree until you get to the root. And as I said before, the idea is that this root is then a succinct commitment to the whole large piece of data that we have, and we can store that off. We can store the root on chain. We can store the tree itself off chain somewhere. Again, dependent on bearing in mind the things that I've just mentioned about where they're storing it. Some points about using things like Merkle trees and maps. Why do we use Merkle trees? Well, because of this useful feature that they have, that they do provide a commitment to data, and because they involve hash functions have collision resistance, so we can be sure that that commitment that we have uniquely represents a certain set of data. So they are very useful structures and very useful techniques. But do remember, these are just data structures. And so we are, what I'm going to talk about today as well is concerned with looking at things more widely, I suppose, as well, and not just the actual data structure that we need. And in fact, we could say that we can still discuss some of these details and be a little bit more agnostic about perhaps the type of data structure that we have. But having said that, Merkle trees do tend to, or maps do tend to be a very useful data structure. One drawback that we have generally is that obviously they require us to do a lot of hashes, which means that a hash function then becomes a bottleneck. And we see this generally in zero knowledge systems, that they're often a focus of research, and because if you can reduce the cost of a particular hash function, maybe introduce a new one, or one that is more ZK friendly, or more it's better in a circuit, then this is going to have a good effect generally around on the total cost of your building your Merkle tree. Okay. So this is just a few details then of if you're going to use Merkle trees, how we can do that. There's a link there to the documentation. We have the Merkle tree type, and this will give you, when we create these, we specify a certain height, and because they are binary trees, then that gives us a certain number of leaves, and so yeah, we store the root in our contract. So this is just some example code here. I think you're all familiar with this kind of thing. We can create a tree. Also, then we can get we use witnesses as well to show values at points in the trees as well. And so this is just a simple bit of code to show update how to update a particular leaf in the tree there, and then send that to a transaction. So very, very straightforward. This is what we would have in our contract. So there you see, as the state, we're storing the tree root, and that then we're seeing that that's a commitment to the whole of our off-chain storage, and so we see that as sufficient. Okay. All right. So that's using a Merkle tree. We can also use a Merkle map rather than having to specify the index of a particular leaf that we're interested in, then we can use a key for that. But other than that, it's a very similar approach. Also, some people have created other libraries as well. So there's this one, that is giving different types of Merkle trees as well. So that's something you may want to have a look at. Okay. All right. So that's what I've sort of talked about so far. Is very much I guess, a traditional, very standard way of keeping some state by taking it off chain and into some kind of Merkle data structure. And that's I mean, that's okay, I guess, but as we've seen already, you start, if you're thinking about doing this, sort of productionizing this, then you're going to, there are a number of concerns that you're going to have to think about. So is there anything that, could we do anything on chain? Are there other techniques we can do on chain? Well, there are some things that people have come up with. So there is one.js pack, which you can use, which is really just saying, well, we have our storage available in our contract. We have those 8 fields, but can we just make sure that we're using those as efficiently as possible? And so to do that, we have this that will help us pack as much data into each field as we can. Obviously, that only goes so far. You can, there are limits to what you can do, but it's certainly a good thing to think about. Maybe a way of making things a little bit more optimal. So that's one potential technique. Other things that people have done that I wanted to talk about, and there's a link there to some discussions about that. One is the idea of having multiple contracts. So if your contract has a certain amount of state, then rather than having your whole application represented by that single contract, then maybe you would spread out your application into multiple contracts, therefore giving you more state overall. So you could think of this perhaps, I don't know, if you had maybe each user would have a certain number of items that represents their state, then in theory you could create one contract just for each user and have that, and do some kind of factory pattern or something like that to sort of put out these contracts. Other ideas as well is the fact that, and again, you have a look at the discussion about this, because I think this is something that hasn't been sort of widely done, but it comes back to the tokens. And I think last session I spoke about tokens, the fact that we have state available in tokens as well, so you can mint a token and then have that have state involved in that as well. So this is quite a clever technique that you can use also to get state on chain if you need to do that, and to give your application, I guess, or your project more state. Although I think these ideas could do potentially work, the big problem that you get if you do, well, these last two ideas, I'm not criticizing the packing idea, but the last two, one problem that we do face with this is then the fact that we're moving away, or we're moving away from this original idea that we want to limit the amount of state that Mina is using because of all the good things that we have with the succinctness. And so if we start to increase the amount of state, then we're going to lose some of that, some of those advantages. And particularly because what we're talking about here would be really, if we're not increasing the state because we have more applications, particularly, it's more a case that even with the same number of applications, we are increasing the amount of state that they are using. So it's not, although, potentially we could do this, I'm not sure it's necessarily a good idea. And so it does still seem that it's probably going to be better to be looking at keeping our state as much as we can off-chain. Okay. All right. Now, what problems do we get with that? Well, I've already spoken about some that are more to do with decentralization and the sort of the security aspects and the production aspects. But one that will be, I think, sort of fairly familiar to you generally, because it very much comes into the what you need to do as a programmer, is around concurrency. Now, this is not something new to blockchain or anything like this. I mean, concurrency is a general concern within computer science, and I mean, in fact, blockchains have been quite remarkable in that they do have techniques in which, in a decentralized way, we can come to agreements around concurrent updates to state. So this is very much what blockchains are concerned with. But if we move our data, our application data, off chain, then we have to decide how do we cope with the scenario where multiple people are going to be updating this state independently. So they're going to have some local state, they're going to be updating that and then providing an update to that that is going to go on chain. And what happens when that update goes on chain is that there are preconditions. We're looking at the previous state and we're checking that the transition that we're making is from that previous state to the next one. But how can we have multiple people doing that and doing that correctly? And how do we decide the ordering, etc.? So this is a potential problem. And one way that this is handled and where we have support for in O1.js is with the notion of the action and the reducer. The idea that well, it goes into quite a bit of details here, but what we do is we say that, okay, when we're doing our computation off chain, what we do is we're making some intention to change the state. So we're going to be doing a particular action of moving from one state to another. But what we would like is to be able to get a number of those together and understand, how we can apply all of those and do that in a consistent and agreeable way. And that is where the reducers come in that they can then take potentially, a number of updates that will be happening to the state and then reducing that into one update. So what you are doing effectively is saying that we have some pending actions, or these are the changes that we want to make to the state, and that we are kind of batching these together by using a reducer, and then that produces a sort of final update as a result of all of these. And I went through this, I think, in the first session, but there's an example here again of this. So you get all of these potential updates that you want to do, and then you can reduce those and then provide one update. So that is one way that we can address the concurrency problem. But what people have found is that this this doesn't scale very well, and also you get limits because of the circuit size. And if you remember, I mean, last week we spoke about this in relation to recursion, and in fact, I think there's some details further on about this. But yeah, we obviously, you know, that there is we have limits on the size of a circuit that we can use, that we can, you know, have doing our provable computation, and so that is going to be a limit to what the reducer is able to do when it is creating this batch of actions. And also, you know, this has to be happening somewhere as well. But this certainly is possible. But do have a look at some of the issues, some of the things that people have said about this. But this is certainly one way of approaching it. But I'm going to talk about some other techniques as well, and look. So the first few here, there's more discussion. This is things people have been discussing on Discord. So one of them is around recursion, and so using that within the reducer, which helps with things like the circuit size, because with we can use recursion to have a small circuit and then apply that repeatedly. There's other proposals as well, by looking at different types of actions and handling different types of actions differently, depending on. I think this is to do with the potential cost that this would have. So to try to get around some of the performance problems that you get. So these workarounds here, these are really around, can we move sort of the action reducer idea? Can we move that forward and do anything with that to keep it going and to make it a little bit more scalable? But what I want to come on to now is to sort of take a step back and say, well, maybe there's a different, you know, maybe a different approach, and that, you know, to see how this ties in, then we need to take a step back and look at sort of blockchain theory at a bit of a higher level. So I just want to talk then a little bit now about what are called modular blockchains. So this concept is more recent. So, you know, back when Bitcoin came out, that was, you know, there was a single blockchain, and Ethereum came out, there was a single layer one, and that was it. You weren't thinking about that, you know, Ethereum environment being split up in any way. You thought that particular chain was going to do everything. But what people have found is, well, partly because, well, yeah, probably mainly because of scalability, I suppose, is that this is not necessarily a good architecture, and that a particular blockchain does a number of different things. It has a number of features, a number of concerns, and that what we can do to make our blockchains more efficient, more scalable, is to try to split out these concerns and to have specific chains optimized to focus on particular concerns. And so this diagram shows that that type of idea. And so it's splitting it out and saying there are three main things that blockchains will do. Well, smart contract blockchains will do, and we can split those out. And those features, those concerns, are execution of contracts. That's the actual computation. The settlement, the consensus, which is really the around the security of and the agreements about the state change, and then the data availability, which is what we were talking about earlier, where we say where can we find the data that we want to make sure that our chain is working correctly. And so people have started to build chains that focus on these specific areas, and some of these are the roll-up sort of base chains that came out of the drive for scalability that Ethereum had. So a lot of these chains are very much focused on the Ethereum ecosystem, but not exclusively. You do have other ones as well, and people are starting to look at looking more widely than Ethereum. So someone had a question about Celestia earlier. That is seen as providing things like data availability, but also settlement for chains, just generally. So it would be, any chain could go to this and get that service from there. And then also we have chains such as the Starknet, which is very much about focused on the execution, and then that goes to other chains such as Ethereum for the settlement, the consensus services that it provides. So this is, I think, the direction we're going in generally. Now, Mina was very much, I always felt it was very much kind of a little bit on its own, and it was sort of forging its own path in the world, and wasn't caught up in what was happening in Ethereum as much. But I think these ideas also apply to Mina, and we shall see these ideas coming in and people taking advantage of these types of things, which is really what I'm going to talk about next. There's some more details there if you want to read sort of the article, an article about this split that's happening. I think this is a general trend that we are going to see in blockchains over the next few years. So let me just check the questions. Okay, I think people are answering their. Oh, thank you. It's very kind, Will. And thanks, thanks Michael, for the details about so showing how yes, hitting the size of the limits for the circuits. So it is a concern. So what can we do about it? So the way that, and again, I apologize, I'm kind of heading back to the Ethereum world for this, but it does provide a background. It does show one approach to solving some of these things, some of these concerns that we are now seeing also happening with Mina. So it's giving us some useful architectures or designs in this area. So what we saw happening with Ethereum is we had these layer 2 chains, these additional chains that were focused on execution, and they took some of the load away from Ethereum, and in doing that, they were able to provide a chain that was faster and cheaper than doing things on the layer 1 chain. And so if you look at some of these now, this is just a screenshot from I can't remember now, DeFi Lama probably, showing some of the more popular layer 2s and the types of chains that they are. So there are different types, but very much based on roll-up technology. In fact, Ethereum is its future is roll-up centric, as they say. So, but there are different ways of doing that. There's the ZK roll-up, also the optimistic roll-up. But that's very much where Ethereum is going, and it seems to be working well for them. It's taking the load away from the Ethereum mainnet and providing faster, cheaper environments for people in which to run their applications. So what kind of things are involved then in one of those, in a layer 2? Well, this diagram from Arbitrum shows you some of the components that you tend to get. So they are okay, they're different chains, but they do have a lot of similarities and a lot of sort of common design features. So what typically happens is that you start off, your application is producing some transactions, and they will come into what is called a sequencer, which is really controlling the layer 2. And that is controlling, coordinating what is happening, and is responsible for getting these transactions, batching them together, and depending on the type of roll-up, it may be also are required to create zero knowledge proofs. We don't with Arbitrum, because that's not a ZK rollup, but it is concerned with batching. And in fact, it is the fact that it can do this batching that is one of the ways that allows us to reduce the costs of transactions on these chains. So we can batch our transactions, we can compress the amount of data, and then the details of this and the state transitions that we're getting from these transactions happening, these then get posted onto the layer one. So the layer one is acting there as a very secure place for providing the settlement, the consensus. So by anchoring the details of these transactions on the layer one, we're getting the security, which means we don't have to provide that as much on the layer two. That's Arbitrum. With ZK Sync, that's a ZK rollup, so it's slightly different in that they have a prover that is taking the computation that is done in the transactions and creating a zero knowledge proof out of that. That is sent to the layer one, where a contract verifies that and says, yes, that transition on layer two was done correctly. Now, one thing that you do need to be, or a few things you need to be aware of, but one thing that is shown here is you've got this thing called forced transactions. And this all comes down to the role of the sequencer here. And what we have at the moment is typically in the layer two chains is that we have one sequencer, we have a centralized sequencer. And this is understandable in that the projects producing these wanted to get their projects up and running. And so, a way to do that simply was to have one sequencer that they controlled, that could coordinate everything, that they could make sure was working correctly. But if you do that, then the people who are using it, the people who are sending the transactions, have to trust that sequencer and trust that it is behaving itself and it's not, for example, censoring transactions. And one of the potential problems that you could get would be if one of these layer two chains decided that they didn't like certain transactions, and in fact, we can look at a specific example here where if you think about what is happening with Tornado Cash and the fact that this is on the layer one, but certain transactions are being censored by validators on Ethereum. So you could get a similar thing with the layer twos, that the sequencer could decide to reject certain transactions. Now, the reason we have this forced transaction is that what we want to do is to give the user confidence that any assets they have on the layer two can be bridged back to the layer one if necessary. And that is what this path here is meant to show, is that there is an alternative path that they can force a transaction to withdraw their assets onto the layer one against the will of the sequencer if they want to. So it's really to provide the user with some confidence that the sequencer is not going to be misbehaving and do malicious things. So that's just something to be aware of about sequencers generally. Now, this idea of taking transactions and batching them up and then posting them to another chain, we've said here, this is our layer two compressing data onto the layer one. Well, why stop at layer two? Why don't we just keep going? And that's the idea that people had when they coined this phrase with fractal scaling, which is, why don't we build layer threes or layer fours where we just do the same thing again and again? We have all these chains batching transactions together and posting them to the layer below. And if there's an advantage to do this from layer two to layer one, then surely they'll be the same, or there should be an advantage from layer three to layer two. Well, in practice, there is a it's not going to work, forever. You can only go so far with this. But people are thinking of this. But what people are thinking of, and where we're seeing particularly layer threes being built, is where they want to design a chain that is very specific to either one application or one type of application. And so we're seeing here the idea of what are called app chains, where the chain is very much optimized to a particular application, maybe because they've adjusted the block time so it will work very well with that particular application, whatever it is. And so you're seeing that now. But that phrase app chain, it doesn't have to mean an L3. It can also refer to an L2. It's really just the idea that you are optimizing a chain to be more, do something more specific. But we are seeing that. We are seeing L3 chains being built. And what we're seeing as well, or starting to see, is this idea of being able to spin up chains on demand. And so there's, going back to the optimistic roll-up idea, so there's the optimism chain. So what they're building now is a thing called the OP stack, where what it allows you to do is to spin up multiple chains, sort of multiple layer 2 op chains, you can see here, which will then all connect back to the layer 1. But also they will have some means of talking to each other as well. And again, I think this is another area we're going to see more development, looking at the way that all of these chains that are being built in the layer 2s, how do they coordinate, how do they communicate with each other? And I think this is also something we're going to see with Mina as well, the idea of being able to spin up chains, spin up app chains that could be useful. Now, some of the things that we should think about if we're thinking about layer 2s, and we've sort of digressed to more general layer 2 ideas here, but some of the points to consider. One of them is around the finality for a transaction. So if you start a transaction on the layer 2, when do you regard that transaction as final? And I think it's always the case that faster finality is better. You want your transaction to be regarded as final as soon as possible. But the problem we have with, for example, ZK rollups is that can be, even more so optimistic rollups, but one of the problems we have with them is that can be quite a long time that you have to wait before that transaction appears in the, is accepted on the layer 1 and is regarded as final. And so what some people do is to say, well, here's my application, is sending a transaction off to the sequencer. So here, here's my transaction going to sequencer. Well, once the sequencer accepts it and, maybe does a little bit of validation about it, or maybe starts to include it in a batch, then I'm pretty confident that my transaction is okay. So at that point, I'm going to regard it as being final. And some applications may decide to do that. Of course, if you do that, then you're taking an operational risk that the rest of this process could fail and your transaction could end up being in a different block or being dropped for some reason. So there is a potential downside for that, but it does mean you can do things more quickly. The other idea here about assets and censorship I've already mentioned, but it is definitely a concern. And what the established rollups are doing for the Ethereum ones is they're moving towards decentralized sequencers. So the idea that people will be able to spin up their own sequencer. Obviously, there'll be security around this. There will be incentives for people to do this securely, and people will be penalized if they don't follow the rules. But that's sort of where people are going generally with the idea of layer 2. Okay, so having said that, that's what we've seen happening in the Ethereum world, and this started a few years ago, so there's been quite a lot of development in this and progress. So is this something that could help us as well? And can this help us with the problems that we're facing? Well, so the answer to that is somewhat mixed, I think, in that we shall see that, yes, it can help us, and we're going to look at some projects that are using this general type of architecture and creating chains that are then linking back to the Mina, the layer one. But you do have to think carefully about what is this helping with. So part of it, if you do this, then yeah, maybe you will get some of the general advantages that layer twos tend to provide. The idea that you can create more optimized chains, because the layer one chain is being built and has to be very generic. It has to be able to cope with any type of application and do all of the functions that a blockchain needs to do. Whereas with a layer two, you can pick and choose. You can then optimize it. You can customize it for working in a certain way and get advantages from doing that. So from that may mean that you could get, for example, faster transactions. You could get shorter block times. Maybe you could reduce the fees that are involved. Does it help us with off-chain storage? Well, where I think that comes in is particularly in the role of the sequencer, because what we're getting is we have some process here that is taking these transactions, and because and here I'm talking about a centralized sequencer, because we just have one of these processors being involved, then it can easily come to a decision about the changes of state and the ordering of transactions. And so that can simplify, and that can help with some of the problems that we're seeing. Okay. It should also be mentioned as well, actually, this ties in also with MEV, if you're familiar with that this is a general problem with blockchains that involve state and computation. The fact that the person who is deciding the order of transactions, this gives them the potential to extract value from that chain. And so if we do get, if we do have a centralized sequencer, then and that sequencer has a mempool, which is the case usually, then again you're getting the potential for that happening as well on your chain. Okay, but let's move away from the theory a little bit and look at some of the projects that have happened. And I think we are very much very early days here in what is happening, and the projects that are coming out with Mina, but people are starting to look at this, and they seem to be having quite a bit of success. And I'll go through some of them, and as I say, I'll just look at ProtoKit, which is what I wanted to really concentrate on. But I'll give an overview of that today, and then I'll look at it in more detail next week, because I think that is perhaps one that has the most potential at the moment. But other ones we have here. This is Anomics. I'm not sure how exactly to pronounce that. The idea that focused on the general sort of layer 2 architecture that we've had. Again, I think pretty much all of these projects came out of the builder programs or the ZK Ignite program. So there's some links to that there. The one thing I did to say was when within your layer 2, again, you're customizing the way it works. You can make decisions. Part of that customization can be the question of privacy as well, and the privacy of state. So you can make a decision about that, whether you want some public or private state in your layer 2. And you see this, in other layer 2s, not just Mina-based ones. So, for example, with Starknet, that is a public layer 2. There's no privacy, but people are thinking of writing layer 3s that have private state. And with where Aztec is going, they're going to have private state in there. So this is potentially possible within your layer 2. So Anomics is the idea there is to do that. And again, if you are If your state is being held off chain, then this is potentially much simpler to do. If your sequencer is not open to people seeing the details of the state that it is using, then you can keep that, you can keep those details private. You can have your private inputs, etc. So that is what they are doing. Batching of transactions is kind of a standard thing that you would do in a layer 2. An interesting point here, the UTXO model. It seems to be that a UTXO model, it generally seems to work better in zero-knowledge applications than an account-based model. For example, Zcash, the original Aztec, these all used UTXO models, and techniques such as the nullifier pattern, which I think I spoke about a couple of sessions ago. It does seem to be quite a useful pattern when you're doing ZK applications. Other details, so yeah, they have a sequencer which does the normal things, which is to pick up the transactions from the applications, to do some validation on those, to store the data that is involved there. Again, this here we start to think about the data availability layer. This could be the layer 2 itself. You could be storing the data in the layer 2, or you could be sending that somewhere else. Again, these are the customizations that you have. Then they want to batch the transactions. So they want to get a number of transactions together and create a proof, a proof of the validity of the state transition they're going to make. And in order to do this, they use recursion with 2 different types of circuits, so they can do that. And I took this diagram, I think, from their repo. I hope it's clear enough for you. But the idea is that we can prove what is happening at a different sort of levels. We can prove the correctness of the transactions being computed, and we can also prove the correctness of everything being batched up together and aggregated. And all of that can then get batched together and sent off to the layer 1, which here is represented on the right with these gray blocks. One interesting point you get about this kind of design is that you don't get with the layer 1 is that the nodes that are the layer 2 nodes can look at the layer 1 to check the validity of their own chain, because they can query the layer 1 to see that the proof has been received and validated for the correctness of the state transition. So that's kind of an advantage they have over the layer 1s, where it's all sort of contained and you can't look elsewhere. Okay. I'll carry on. We're running out of time slightly, so I'll keep going. The details of the storage they have. So they're using trees. Just some points about this. I'll do quickly. This is very similar, a similar type of design to the things you'll see in Zcash. We have the idea of the transactions representing the unspent transactions, the value that a particular user has. This is held as what is called a note, but to obfuscate that, we actually hold a commitment to a note. And then to prevent double spending of these notes, we then have a nullifier. We use a nullifier pattern, and the nullifier is held within a separate tree. And what we can do is that when we want to spend one of these notes, the commitments to those notes are held in a data tree, when we want to spend one, we go and check the nullifier tree to make sure that this note hasn't already been spent by looking for a nullifier for this particular note. If it's not there, then we're okay to go ahead and spend that note. And what we do is we create a new note and put that in the data tree, but that note then has a new owner, and that represents a transaction, a transfer of the value of that note from one user to another user. Now, this idea, I'm assuming this is the same for anomics. The way that this works in Zcash is certainly is the case that we don't remove items from these trees. We just append to the trees. So you have to be careful if you're doing this to have a large enough tree that is going to be able to hold all of the notes and all of the nullifiers that you're ever going to need. So it can mean that you're going to end up with a very large tree, which in effect means a very deep tree, which then means the proofs that you need to show that something is within your tree are going to be larger. So that's something to be aware of. Okay, so that's anomics. Another one, Zico. I don't know as much about this. I got this image just to show that they're looking particularly at games, I think, but generally what they're thinking about, I mean, they do focus on they do address the idea of the data availability, and what they're using for this is a chain on Cosmos. So Cosmos is an interoperable chain, and there is you can add your own chains to that. There's a protocol for doing that. There's one type of chain, the Ethermint chain, which is an EVM compatible chain based on the Tendermint consensus. So that's what they are using here, and that's what they use for their data availability. So that's where they're publishing data of the transactions, and that gives them reasonably quick finality. But this is just the first approach, and the way it works is that the data that is being received gets batched. The validators sign this individually. Those signatures get aggregated, and then that gets posted to the layer one. So that's where you get the security. And the validators in this case are run by O1 Labs and the foundation, etc. So they're seen as trustworthy organizations. But this is just the initial approach, and I think eventually they're going to use Celestia as the chain to go to. Okay. Now, ProtoKit is one I think it's perhaps where we're seeing most happening at the moment, and certainly the people involved. They came out of I think it was a ZK Ignite project where two people had kind of similar ideas, and they realized and then merged and worked together and produced quite an ambitious project, a layer 2, and they're doing a great deal on it. They're very active on Discord, so you can go and chat to them about this. I've put some links there to an introduction to that. There's also a thread on Discord about it, sort of giving you a general overview. It is the general idea is that it is a sort of producing a layer 2, and what it's trying to do is to provide this for you so that when you're writing your application, you can use this and you can write your application on ProtoKit, but also it's not only there to provide some sort of scalability, but it also they've abstracted away some of the details about the storage. So they provide, rather than you having to get involved in the nitty-gritty of the way that the data is being stored, they've tried to sort of provide an API to abstract that away to make it simpler and to allow you to concentrate more on the business logic. But then in addition to that, because they have a sequencer, that allows them to address this problem that we were seeing with the sort of the action reducer problem, because it means that they can allow the sequencer to make decisions about the updates to the state and to enforce that. They have different data structures sort of behind the scenes, and a database behind the scenes to be storing the data. That also means then that they can provide services such as GraphQL to allow you to query that data. Okay. Another thing that they allow, which is important generally particularly in zero knowledge blockchains, is the idea around failed transactions. And this has been problematic with some chains generally, because if a transaction fails within this process where you're creating proofs of the correctness of computation, then that doesn't necessarily fit very easily with that proof and how that proof is being sent to your layer one. So different chains have handled this differently, but I think with ProtoKit they've managed to do this. And what you want to do is to be able to include, to have a proof that says, yes, this particular transaction failed. But we did sort of compute that transaction correctly, but it failed. For example, if you were trying to transfer tokens that you don't actually have, that could be regarded as a failure of a transaction, but you want to be able to prove that that was done correctly. And if you don't do that, you get sort of into denial of service problems, etc. Okay. I'm going to have to, I'm coming to the end of my time. So there's just some details here. They have a starter kit that you can use, and you just clone that and install the details, and then you can spin it up. I just did that quickly here. I ran the tests here, and you can see this is a very simple example from the starter kit of what the type of thing that you could write. And so you do need to be aware that, I mean, some of these objects that you're going to use are from O1.js, but then some are from ProtoKit itself. So you do need to be a little bit aware about that, such as the assert. But you can see here, you have this idea of state here, a sort of general concept. You can decorate like this. So here we have some balances that we're going to hold the state of. We're going to have this in a map. So, as the sort of typical design where you're mapping from a public key to a number. Here we've got a uint 64, and that number is the balance that a particular public key has. So here we have that mapping in this variable balances, and that's what we're holding state. But we can write that just in this very general way here. We're not having to think about behind the scenes, how is this actually being stored. We can just write it like this. We also have the idea of a circulating supply as well. So the sort of total supply, total number of tokens that are available. Okay, I'll let you have a look at that, because I just want to very quickly. Sorry, I'm out of time. I just want to very quickly talk about the challenge, and I'll come back to ProtoKit next time. So just quickly talk about the challenge. I think this is fairly straightforward. There's not very much involved in this. I think you should be able to do this quite quickly. But the idea is with the challenge is that we're getting messages that they're coming in sort of in batches, and what we're trying to do is to validate the details in the message, and each message has a number associated with it, and then some details within that message. And what we want to do is to create a program that is going to keep track of the highest message number that has been received and correctly validated. So you need to do some validation on the message detail. So there's some rules about that. The numbers have to be in the correct range. We have this X and Y location that have to be in a certain relation. And then there's also a checksum as well within the message to check that the values haven't become garbled. So you have to check all of that. Sometimes you don't have to do all the checks. So you need to be aware of that. If the ID is 0, you don't need to check the rest of the message. If the message that comes in is incorrect, then you can just drop the message. You don't have to do anything special and just go on to the next one. Also, if the message number you get is lower than the previous one you had, that just means it's a duplicate, and you can still process the message, but you don't need to check it. You don't need to throw an error or anything. But the idea behind this challenge is that you want to keep the size of the circuit that is checking these messages. You want to keep that small. So you need a way to do that, and to have this application able to take in a number of these messages where we don't know how many messages we're going to receive. It has to, we have to be able to process a variable number of messages at a time, and do it in a way that is not going to be hitting any kind of circuit size limit. So we want a small circuit, and we want to be able to respond to the number of messages that are coming in. And then the only thing that we need to persist around all of this is that we want to just keep track of the highest message number that we've got. So we know the kind of the last message that has been received. So if we wanted to restart, or if somebody else wanted to carry on, they could start from that point. Okay, so I think it's very straightforward. I think you should be able to see the kind of design I'm asking for there. But as always, if you have questions, please do ask. I'm out of time, so I'm going to stop sharing. Let me go back to the meeting. Yeah, I'll finish there. Thanks everyone for attending. I hope you enjoyed that. We'll do lots more about ProtoKit next time, and I shall see you then. Please ask questions on Slido, or put them into Discord, because otherwise I'm liable to lose the questions. All right, thanks everyone. I hope you have a good rest of the day, a good weekend, and I'll see you in a couple of weeks. Thank you.
Thanks, Lawrence. Bye.